Welcome back. So last week we explored what deep learning is and where it fits into the world of AI and machine learning. And this week we're going to build your understanding from ground up. We will introduce the core learning framework behind deep learning, which is supervised learning. And we'll take our first real look at models, including linear regression and the perceptron. So by the end, you will see how these pieces fit together to form the foundation of modern neural networks. To understand how deep learning works, we need to begin with supervised learning. This is the most common type of learning used in deep learning today. So in supervised learning, the model is trained on pairs of input and output, right? So in and out. For example, an image and its label, right? An image and the label could be a cat. And the model learns by seeing these examples and adjusting itself to make better predictions, right? So why do we start here? Because this idea of learning from labeled data is the same principle that powers nearly all deep learning systems. So supervised learning problems generally fall into two main categories: regression and classification. So in regression, the goal is to predict a continuous value. For example, we may want to predict the price of a house based on its size and location, right? The output is a real number, and we usually evaluate performance using metrics like the mean squared error, right? Mean squared error. Now, in classification, the task is to assign an input to one of several categories, or what we call labels. So a common example is handwriting recognition, right? And the model takes an image of a digit and predicts which number it represents. So this is an example of a classification problem. And so understanding here the difference between classification and regression is important because it determines not only what kind of output the model will produce, but also it will define things like which activation function to use and which loss function to use later when we introduce these two. So in supervised learning and especially in deep learning, we don't just throw all our data into the model at once. Instead, we split it into three parts. So the first one is training, the second is validation, and lastly, testing set. So during training, the training set is what the model uses to learn patterns. It's the only data the model sees during the weight adjustment process, as we will see. Whereas for the validation set, it is used during the development stage to simply validate or evaluate how well the model performs on data that it hasn't trained on. So this helps us tune decisions like the number of layers in the neural network, the learning rate, and other parameters which we will discover later on. And finally, the test set is a strictly holdout set that we only use once and at the very end. So it is our honest check. Can the model generalize to completely new data? So think of it like this. You practice on training data, you check your progress on validation data, and then you take the final exam with the test data. So now that we know what supervised learning is, let's take a look at one of the simplest predictive model. It is linear regression. So linear regression is used to predict a continuous value, right? And as an example, trying to predict the price of a house based on input features such as the square footage, right? The number of bedrooms, the distance to downtown. So the model works by computing a weighted sum of the input features plus an extra term, which we will call later the bias, right? So mathematically, this looks like this equation right here. So each input here, each x here, right, the x's, represent a feature, right? So x1 will be the square footage, for example, and x2 will be the number of bedrooms. While the w's here, or the weights, they represent how important that feature is in making the prediction, right? So the bias is an extra term which we will introduce later and discuss why is it important. So understanding linear regression is important for those who haven't had the machine learning course before, because it introduces the core concept that neural networks build on, right? So the concept of combining inputs and weights and bias into an output, right? So linear regression is the starting point for learning how models can map data into predictions. Once our model makes a prediction, we need a way to know how close or how far it was from the correct answer, right? That's where the concept of an error comes in, right? So the prediction error is simply the difference between the model's output, right, which is the y hat right here, and the true label, which is the y here. So for example, if a house is worth 500K and our model predicts 480K, so then the error it's minus 20K. If it predicts 510, and then the error is plus 10K, right? So these differences tell us how well the model is doing and how, more importantly, they give us something to use as a feedback, right, for our model. And in machine learning and deep learning, we use this feedback to help the model improve over time, right? If the prediction is too low, the model learns to adjust upwards. If it's too high, it learns to adjust downward. And then this process of observing, measuring, and responding to error is at the heart of all the learning process of all supervised learning models. So now that we know what the prediction error is and what it means, we can ask the question of how do we summarize and sum up all those individual errors into something the model can use to learn, right? And the answer is a loss function. That's the job of a loss function. So loss function is a mathematical tool that aggregates the prediction error, right? And so it sums up and aggregates all the prediction errors across all examples in our data set into one single value called a loss, right? So you can think of it as a score that tells the model how well it's doing overall, right? So a high loss means the model is making large mistakes, and a low loss means the model's predictions are really close to the correct answers. The loss function is really critical because it's what we try to minimize during training, right? So in other words, the entire learning process is about finding the model's parameters or optimal parameters that result in the smallest possible loss, right? So later we will explore how the model uses this loss to adjust itself and adjust its own parameters, right? But for now, let's remember the loss function is the bridge, like the bridge between raw prediction errors and the actual values. So one common loss function, and the simplest one, is the mean squared error. So it simply squares each error. So bigger mistakes will count more, right? So then it averages them. So this helps the model focus on reducing large errors during training. So linear regression, as we've introduced it, it is a good predictive model. It is powerful for simple linear problems, but it has a limitation there, which is obviously the linearity, right? So it can only model linear relationships, right? It has a linear decision boundary. This means that it's really suited for problems where there is a relationship there's a linear relationship between the input and the output, right? There's the relationship between input and output is a simple straight line, right? Or a plane in higher dimension. But real world problems actually are non-linear, right? So for example, predicting whether a tumor is malignant or benign, or identifying handwritten digits, often these are complex problems that don't have really a linear relationship between inputs and outputs. So this is where we need more complex models. And we can start before we get to more complex neural networks architectures. We can start simply with the perceptron, right? So a perceptron is really the first building block of neural networks. It builds on linear regression by simply introducing something new, which is called an activation function. Okay, so instead of directly outputting the weighted sum, so when we say the weighted sum, it's simply z equals the weight times the x plus the bias, right? So instead of simply using this weighted sum, the perceptron passes the output through a function which transforms the result in a nonlinear way, as we see in this figure right here. So this small change has a big impact. It allows the model to learn more flexible, curved decision boundaries, as you can see here, right? And therefore to represent richer relationships between features and outputs. So the perceptron is often called the simplest neural network, and it is really the first step toward building much deeper and more expressive models. So if we want to define the perceptron, we can say it is one of the earliest and simplest types of artificial neural units. It takes multiple input features, each multiplied, right? So these are our features, x1, x2, and x3. Each is multiplied by a corresponding weight. You can see the weights right here. So then these are summed together, and a bias is added. We'll talk about this bias later. And this gives us a value z, right? Which we can think of as a raw score for the prediction, right? And then instead of using that raw score directly, we apply a step function, right? This is a basic activation function used for binary classification. So as we will see, the step function can simply be if the z is positive, right? Then we predict class 1, otherwise we predict class 2. This is a simple threshold to make a decision, right? So in this way, think of the perceptron as a thresholded decision maker, right? So it draws a straight line in the input space and classifies points on either side, right? Either class 1 or class 0. It is a simple idea, right? And it simply turns a weighted input into a binary decision, right? So if we want to define what a bias is and why do we add the bias term, it actually plays a very critical role in how perceptron and also neural networks make predictions. So just like the weights, the bias is a learnable parameter. We also learn it from the training data, but its job is slightly different than the weights. So it allows the model to make predictions that don't have to pass through the origin, right? So you can see here in this figure, this is the straight line without the bias. It always has to pass through the origin. Whereas if we add the bias, we can shift the line up or down or move the decision boundary left or right depending on the problem, right? So more generally in higher dimensional space, the bias allows us to position the decision boundary in a way that better separates the classes or fits the target values. So you can think of the bias as the model's default output when all inputs are zero. When all the x's are zero, all you have left off is the bias, right? So that default needs to be learned, just like the weights, right? We learn the bias term from the training data. So how does a single perceptron classify inputs? So imagine each input point as a position in space. Then the perceptron takes in all the input values, multiplies them by weights, and then adds a bias and calculates a single score, as we said before, right? And then we pass that score through what we call the step activation function that outputs 1 or 0 depending on if the score passes the threshold of a 0 or no, right? So geometrically, this is like drawing a straight line or a hyperplane in the input space, right? Just like this one. So the perceptron classifies all inputs on one side of that line into one class, the blue class here, and everything on the other side into the other class, the red class right here. So this is why we say a perceptron can only learn linearly separable data, because a single line, straight line, can't divide the classes. Then the perceptron won't be able to separate them correctly, right? And that's the exact limitation of a perceptron, and that's why we need multi-layer networks. If we want a concrete example, we can think of a classification problem of a new student, right? We have a perceptron that will predict if a student will pass or fail using features like the number of hours that the student has studied and the attendance rate, right? So let's say after training, the perceptron has learned these weights or these parameters, right? We will get to the training stage in a second, but let's say we've already trained this perceptron and we found this optimal set of weights. So how do we classify a new student? Let's say we have a student who studied for 10 hours and has 80% attendance rate, right? So all we have to do is calculate the z, right, which is the x times w plus b, and here we have two x's, so it's going to be x1 times w1 plus x2 times w2 plus the bias at the end, of course. So we calculate the z. I believe the final value here will be 5.4. So if we compare 5.4 to the threshold of the step activation function, which is 0, so 5.4 is larger than 0. It is a positive output. Therefore, the perceptron's output will be 1, okay, so which corresponds to a passing student, right? So this is how a simple perceptron takes a set of numeric features and turns them into a decision, right? By computing the weighted sum and then adding a bias and then applying a step function, and then comparing it to a threshold, which is usually in this case a 0. Now that we've seen how a perceptron makes predictions, let's talk about how it learns. How do we train a perceptron using training data? So the goal of training is simple. We only want to find the best weights that minimize the average error over all the training examples. So the process starts by initializing the weight, often randomly or with small values. And then for each example in the training data, the perceptron does the following. So first it will make a prediction and then compares it to the correct label, calculate the error, right? You can think of the error as simply the actual class minus the predicted class, right? And then it will update the weight using this simple rule right here. So the new weight will be the old weight. This is new weight. And this is the old weight plus the error, which we just calculate here, times the input feature, right? So this rule is called the perceptron learning rule. It simply adjusts the weights in the direction that would make the model more accurate for that example, right? If the prediction was too low, it increases the weight. If it was too high, it reduces the weight, right? So this update is repeated iteratively for all the training examples, and we do that often multiple times. So we do multiple rounds of training, and those rounds are called epochs, right? So over time, the weights settle into values that make better predictions more consistently. Now that we have understood what a perceptron is, let's take a step forward and see what a full neural network looks like. So a neural network is built by organizing actually many perceptrons into layers. So the input layer right here receives the raw features, the x's right here. So these are, as we've said in the example, could be the square footage of the house or the number of hours studied by the student and so on. These are the x's. So then one or more hidden layers transform the data internally, and then the output layer, on the other hand, will produce the final prediction, right? So each layer is made up of multiple perceptrons working in parallel, and each perceptron in one layer connects to every perceptron in the next layer. So these are our perceptrons right here, right? So this is why we sometimes call these fully connected or dense networks or layers, right? So the data flows through the network layer by layer, and then with each step it becomes more abstract, right? So moving from raw inputs or features to structured patterns to meaningful outputs at the end, right? So while this is just a high-level preview, this concept of layer transformation is actually what gives deep learning its depth, right? So now that we've seen how neural networks are structured, we can focus on how it actually works during prediction. So the most common type of neural networks are called feed-forward, right? Networks, feed-forward. This was supposed to be an animation, but it's not working here. Anyway, I can share it with you later on Canvas. So in this type of architecture, the information flows strictly in one direction, right? From the input layer through the hidden layers and finally to the output layer. So at each layer, the network performs a very simple but powerful transformation. It takes the input from the previous layer, multiplies them by the weights as we just described, and adds the bias, and then applies an activation function. So this process is repeated layer by layer until we get to an output. This entire path is known as the forward pass, what we call the forward pass. Forward pass. So the network doesn't learn or adjust anything in this process. It just produces a prediction based on its current weights. This is an example of a forward propagation or a forward pass. So given a network that has already been trained and we already have learned the weights and the biases, we have a new house right here to which we're trying to produce an output. And the different inputs we have is the features of the house, which is the number of bedrooms and the square footage. These are our x's. And we add the bias term. So we calculate the z's internally, which is the different weighted sums. We pass them through activation functions in these perceptrons. And at the end, we're going to receive this prediction or a decision or an output.